going. So where did we leave off last time? We figured out what the problem is that we're actually trying to study this semester. And then we finished by looking a little bit at the one-dimensional version of it, just trying to get a little bit of intuition. So one thing we learned is that when we solve this in 1D, the solution, the optimal map has to be monotone, right? So in our example of the book moving problem, with quadratic cost, we're going to slide the books over smoothly. I want to say just a teeny bit more about the 1D problem, and then we're going to move on to higher dimensions, starting with continuous optimal transport, just again trying to get a little bit of intuition into what's going on here. So part of the rest of today will be still trying to just build a little intuition, a little bit of language, and then we're going to go back to the Kantorovich formulation and start trying to build things up a lot more rigorously. Okay, so this is where we were. We were doing this in one dimension. We know the solution has to be monotone. Okay, so the solution for the map is monotone. And now the question is, can we try to say a little bit more about the solution and actually characterize it? Can we construct it? Your intuition you can get maybe from the book moving problem is that there it's easy to construct a monotone map. If we start here and we end here and we know things have to be monotone, it means we just really need to keep sliding things along until they reach their spot where you want stuff. And once you reach a spot where you want stuff, you stop. Okay, we can do that in general with more complicated densities than just books. So we're going to do this using the cumulative distribution functions. I'll write down. So let's use these guys. Okay, so what these do is we've got our densities, little f and little g, and what these are going to say is, given any point, how much mass came before us at this point. Okay, so we've got our density. Here's f. I'm interested in, let's say it starts here. I'm interested in some point x. And what the cumulative distribution function is going to do is say how much mass is there up to this point. Okay, so f of x I get just by integrating up to this point. So say from negative infinity up to x. Okay, and capital F is going to be obviously a monotone non-decreasing function, right? Because as we go farther and farther to the right, we gain more mass. Okay, and similarly, we can write down capital G. Okay, now using these, it's not too hard. It's quite straightforward to write down the solution we're looking for. So what are we expecting to happen? If I draw my two functions, so here's my f, and here's some g. I pick any point x, and I'd like to know where this is going to be mapped to. It's going to be mapped to some point, t of x, which we don't know yet. But what do we know? We know we're moving things along in a monotone way. So what I should do, what I should expect, right, is that the amount of mass up to here is equal to the amount of mass that I've gotten up to here, right? If this amount of mass was different than this amount of mass, then I would have taken some of this and had to pull it out this way, which we know we're not allowed to do. Okay, so we expect these to be equal. So what do we expect? We expect that for a monotone mapping, capital F of x should be exactly equal to capital G of t of x. This seems reasonable, right? This is the only way we can do this in a monotone way. There's lots of ways of rearranging this into this, but only one of them is going to be monotone. Okay? And this actually gives us an exact solution. Okay, so t of x we can write as capital G inverse of f of x. Okay, so I mean capital F and capital G, it's not that they have to be nice functions or even things that you can write down using elementary functions, right? But they're scalar valued functions of one variable. They're not hard to work with. Would not be hard to invert numerically, for example, to very high accuracy, right? Just using a simple Newton iteration. If you wanted to code this up, you can do this in a couple lines of code, really. So that's a nice trick in 1D. In fact, it's been used a little bit in practice in some geophysics problems lately, where they say they have data that they want to compare. We'll probably talk more about geophysics problems later on in the semester. But they have some data that they want to look at, and they want to compare it to maybe some simulations, whatever it's doing. Potentially, there's quite a lot of data, right? This may be very large scale. It may be 3 dimensions or even 6-dimensional. So optimal transportation techniques are really, really nice for comparing these, but also very, very expensive if you've got very large scale data. So one trick that's been found to work really well actually is to, instead of comparing all of this, is to say, let's just look at little slices of this. Let's compare the slice of this, or just a one-dimensional section of this, to a one-dimensional section of this, and run through the data this way and solve a whole bunch of one-dimensional optimal transportation problems using a simple formula and basically add up the results. Okay? You're not doing exact optimal transportation, but it ends up giving you a nice comparison that's much, much cheaper than solving 3D optimal transport or 6D optimal transport. So this formula is actually seeing some use in practice now. But of course, it's not so simple in higher dimensions. I can't write down a simple formula like this once we go to 2D or 3D. But we get some of the same properties. We don't get quite monotonicity, but we get some kind of generalization of that we're going to talk about. So that is 1D. Let's try to move up to the continuous problem in higher dimensions now. Okay, so let's move on to continuous problem. So by the continuous problem, I mean we have density functions. So continuous problem in Rn. Okay, again, I'm going to do quadratic cost. So what's our goal? Our goal is to find a map to minimize this cost. Right, subject to our conservation of mass constraint. So F getting rearranged into G, again, looks like if we integrate F over this set, we should get the same amount of mass as if we integrate G over corresponding set. Right, this was the condition on the push forward of the map T. That the push forward of T turned F into the density G that we wanted. Okay, again, just like we did in 1D, we want to try to characterize things a little bit, learn some more properties of what the solution might look like. So let's start here. There's something natural that we could do here, which is to say there should be some relationship between these two things, right? Here, ideally, in some sense, whatever's happening over here is given by t of x, right? Y equals t of x. That's natural. So let's try to do that change of variables. So if we do a change of variables, y equals t of x, what do we get? This guy stays the same. Okay, so now I want to have g of t of x. Now what else goes here? Okay, we're integrating over t inverse of a now, so that's good. We've got the same limits, which is nice. What else? dt of x, yeah. So we need to take the determinant of the Jacobian of our change of variables, right? This is our change of variables formula from calculus. So we want the determinant of the Jacobian. Okay, again, this is under the assumption that things are nice enough that this Jacobian makes sense, but certainly formally this is what we expect. And this should work no matter what set A is, right? A could be any set that lives in my domain, any nice set, and this should work. So that means, at the end of the day, since this is true for all A, what I really expect is that this function here is equal to this integrand over here. Okay, so we expect that g of t of x times the determinant of the Jacobian of my map is equal to f of x. I haven't done optimal transport yet. This is just saying I've got some kind of mapping that rearranges f into g. There's lots of ways of doing that, and all of them, if they're differentiable mappings, are going to satisfy this equation. This is nothing but conservation of mass. Now we want to do more than that. We want to minimize some cost. We want to minimize this quadratic cost. So I'm going to do almost exactly what I did in one dimension. Right? In one dimension, what did I do? I picked x1 and x2, and I said these map to y1 and y2. And now let's try to understand something about it. Let's see what happens if we swap the positions of y1 and y2. We know that increases the cost. And from that, we learned that we got a monotone map. I'm going to do something very similar here, but we've got to do a little bit more work. We've got to play around with it a little bit more. So this is what I'm going to do. I'm going to choose some points. Now, instead of 2 points, I'm going to choose a bunch of points. So let's choose x1, x2, up to x, capital N, say, that live in my domain. This capital N is not the same as the dimension of my space. It's just some number. Okay. Now, again, we're going to suppose that, okay, so let's suppose that T is optimal. So again, at this stage, I'm assuming we have an optimal map that's nice enough. I'm just trying to say what properties must I have. Well, later on, we're going to try to decide if we can actually find an optimal map. So suppose that T is optimal, and let's let yi equal T of xi. Okay, I'm going to again do the same thing I did in 1D. So in 1D, I said I have points x, and I build a little interval around them, right, such that I have epsilon amount of mass living in this interval. All right, or in higher dimensions, so we need to build a ball. So let's let EI be a ball centered at xi. And again, we want to have an epsilon amount of mass in here. So that means that if I integrate over this, I get some epsilon. Okay, and as before, right, I had my little intervals. I looked at where they got mapped to. I'm going to do the same thing here. I'm going to look at what set these e's get mapped to. So let's let fi equal whatever these e's get mapped to. Okay, so let's draw a picture. Okay, so we have, what do we have here? We have these little balls. So this is E1, E2, E3, they get mapped somewhere. Let's call it F1, F2, F3. And now, again, I'm trying to do as much as possible what I did in the one-dimensional case. I'm going to create a new mapping that's still measure preserving. It's the same almost everywhere, except inside these little balls. And inside these little balls, I'm going to just switch things around. So in 1D, I just had to swap these two things. Here I've got more to work with, so what I'm going to do is I'm going to permute them in a cyclical way. So E1 is now going to get mapped to F2, E2 to F3, E3 to F1. Okay, so let's create a new mapping. A new map T tilde that's still measure preserving. Okay, and we want T tilde of each xi to equal yi plus 1. Okay, so E1 again goes to F2. We're doing this in a cyclical way, so once we get to the top, this wraps back around to F1. Okay, the little sets also get permuted. Okay, and everywhere else we don't change things. So T tilde of x is equal to T of x everywhere else. So if x does not belong to the union of all of these balls. Okay, again, not much yet has changed from one dimension. We have a new mapping. It's not going to be optimal anymore, right? We're going to get a higher cost with this, so I can write that down. T tilde is not optimal. Or let me write it this way. The original map T is optimal. I guess by permuting things, I could have kept the cost the same. I certainly haven't brought the cost down. So we know that. If I look at the cost with the map T, it's going to be less than or equal to my new cost with the map T tilde. This should have an F. Right, again, all of the arguments that I did in 1D basically still work here. In most of the domain, I'm integrating exactly the same thing here. So those parts of the integrals I don't have to worry about. I only have to worry about when I'm integrating over these little balls. When I multiply this out, I've got an x squared times f on both sides. Those are the same. I have a t of x squared times f on both sides, t tilde on this side. The integrals are the same because these are both measure preserving mappings. So again, all that's going to be left is my cross terms. So I write down my cross terms, I divide through by epsilon, and what do I get? Doing everything exactly the same as I did in one dimension, I get 1 over epsilon times. Okay, I only have to worry about what happens over these little balls. Okay, so I integrate over my little ball, and I have these cross terms left over. And move over everything over to one side of the inequality. Now again, assuming everything is nice enough here, I can take my epsilon to 0. Okay, so as I take my epsilon to 0, I'm going to shrink in on the center here. So this is going to go to xi, right? T tilde is going to go to yi plus 1. T is going to go to yi. And integrating f over this little ball, we said that has to be equal to epsilon, which is why I've divided out the epsilon here. So what's left? Taking epsilon to 0, I get that the sum over all of these little balls of xi dotted with yi plus 1 minus yi is less than or equal to 0. Okay, in the special case of capital N equal to 2, and in the special case where I was in one dimension, this would be exactly the monotonicity condition that I had before. Now it's a little bit more complicated result that we need. And this is called cyclical monotonicity. So this tells us, let me write it first, cyclical monotonicity. Oh, let me actually write it down for 2 points. So we've got it. What we require is this holds for n equals 2, for n equals 3, for n equals 4, for n equals 5. For any number of points that you choose, this condition has to hold. So it's stronger, certainly, than just plain old monotonicity. But just to give a little intuition, if capital N equals 2, what do we get? We get that x1 dotted with y2 minus y1 plus x2 dotted with y1 minus y2 is less than or equal to 0. Or if I rearrange it, it looks almost exactly like the monotonicity condition I had in 1D, except now this isn't scalar multiplication. So I have x2 minus x1 dotted with y2 minus y1 is bigger than or equal to 0. So, for example, if this was my x1 and this is my x2, and over here were my 2 points that they got mapped to, let's move it a little bit. I know which point is going to go where, right? So what do I know? I know that this vector x2 minus x1 dotted with an arrow that points from y1 to y2, right, is greater than or equal to 0, which tells you what? Their angle is less than 90 degrees, exactly. They've got to make an acute angle. So that means that this is my y1 and this is my y2. All right, if I superimpose these, this is x2 minus x1, and this is y2 minus y1. They make an acute angle. Okay, so this is kind of intuitive based on what we learned from the book moving problem. If these points are here and here, these aren't going to try to wrap themselves back around, right? Again, they're trying to move in as monotone a way as possible, but now, of course, they've got freedom to move in multiple dimensions. So this is part of the condition. Again, this condition, this one here, has to hold for all values of capital N. So it's much stronger. And in some sense, for all capital N, in some sense, it's placing some restriction on how much we can twist mass around as we move it. It doesn't. This condition says we really don't want to twist mass around. We want to try to keep everything pointed in the same direction if we can. So it somehow restricts our ability to twist mass. You've seen probably other transformations or changes of variables before that don't want things to twist or rotate or things like this, right? So what is an irrotational map? Nobody has seen an irrotational map before. Right, so if something is irrotational, Jimmy, you look like you want to answer.
So it can be written as a gradient of a scalar?
It can be written as a gradient of a scalar, right. So this is sort of like saying the mapping wants to be irrotational, but it's actually stronger than that. So this is actually a stronger condition. And in fact, it turns out that this mapping, if things are smooth enough, can be written not only as the gradient of a scalar, but it can be written as the gradient of a convex function. So this is a result by Rockefeller. Okay, so a cyclically monotone map can be expressed, if things are smooth enough. If things are not smooth enough, you have to relax this a bit. Can be expressed as the gradient of a convex function. We're going to actually derive this result later, that we are actually looking for the gradient of a convex function, and we're going to do that using the Kantorovich formulation. But maybe I'll ask one or two questions first. Do you know what a convex function is? People are nodding. Okay, follow-up question to that. What is a convex function? Okay, is this a convex function? Why? Okay, why? Because of the secant lines. Okay, so what's wrong with the secant lines? They lie under the function, right? That's not what we want. Okay, so for a convex function, right, if we draw the secant line connecting any 2 points, it should always lie above the function. Okay, so a function f is convex if, okay, for any x and y belonging to the domain, which better be a convex set, and any lambda between 0 and 1, okay, so what are we looking at? We're looking at the value of the function somewhere between here and comparing it to the value of the secant line at the same point. The value of function is lambda x plus 1 minus lambda y. And this better be below the value of the secant line, which is just connecting these 2 points, f of x and f of y. So this is less than or equal to lambda f of x plus 1 minus lambda f of y. Give you this reminder now. We're going to do a little more review of convex functions, probably a couple classes from now, because it turns out we're going to need a lot of techniques from convex analysis to study this problem. By the way, how many of you took the class in convex optimization that was a year or two ago? A couple people did? You don't need to have taken that class to understand this material, but you'll perhaps recognize some of the techniques that we use. Okay, so what did we learn? If we happen to have an optimal mapping, it can be expressed as a gradient, not just any gradient, the gradient of a convex function. So we can write T equals the gradient of u. for some scalar valued u, where u is a convex function, so this is the part that comes from the optimality condition. The optimality condition says our optimal map looks like this. We also had a condition that came from the fact that we needed a measure preserving mapping, right? And that's where we just did our change of variables formula and said from mass preservation, we had this expression that the determinant of the Jacobian of the map was equal to f divided by g of t. And now we can fill things in a little bit. We know more about t. T is gradient of u. So what do I get? I get the Jacobian of the gradient of u. That's, what's that? The Hessian. The Hessian, yes. So we got the Hessian of u, determinant of the Hessian of u is equal to f of x divided by g of grad u of x. Okay, this is the Monge-Ampere equation. Okay, so this is second order elliptic equation. I'm just going to leave it here for now, and we're going to come back to it and talk about it in a lot more detail a little later on. But this is a nice formulation. You know, it takes this optimization problem and brings it into the realm of partial differential equations. And people have studied partial differential equations in quite a bit of detail. They've studied elliptic PDEs in quite a bit of detail, and it means that we can use the techniques that we know from PDEs to learn more about optimal transport. And we can use the techniques that we know from the numerical solution of PDEs to actually try to construct solutions to this problem. All right, the way it's written right here, obviously this requires things to be kind of smooth enough. It turns out there's a couple different kinds of weak interpretations of this equation, so you can relax assumptions on the data quite a bit. You don't need to have second derivatives or first derivatives at the end of the day. So we're going to talk about that a little bit later. Any questions on that? Yeah. What kind of function spaces will we be looking at? Okay. So as this is written right now, if you want to understand this in a classical sense, you're going to be looking for a u that's a C2 function. If you want to look in a weak sense, it depends a little bit what weak notion you're using, but typically you'll be looking on the space of convex functions. Convex functions, do you guys know how much regularity convex functions have? C0, yeah. A little bit more than just that. So they're actually Lipschitz continuous, or at least locally Lipschitz continuous. So in general, if you're looking at, say, a viscosity solution of this, which we'll talk about later, you expect things to be Lipschitz continuous. We'll have some fun examples where things break down at the boundary sometimes. So in fact, you can write down examples of Monge-Ampere equations where the solution becomes discontinuous at the boundary, which makes the analysis fun and makes the numerics interesting. But typically for our purposes, we're going to want Lipschitz functions. Any other questions on this? So again, this is background. I've tried to give a little intuition into how we got here, but I've also waved my hands a bit along the way, and we are going to go back and try to fill in some of this detail as the semester goes on. But hopefully you've picked up some of these key points that optimal mappings have some kind of monotonicity, cyclical monotonicity in this case, that they're in some sense equal to the gradient of a convex function, we can have relaxed notion of all these ideas, including the word gradient. But let's start trying to make things a little bit more rigorous. Okay, so we talked about how we had kind of two big formulations of optimal transportation. The Monge formulation, which is more intuitive probably to write down, but it didn't always work as well, right? We didn't always have solutions. The problem wasn't always feasible, so this is kind of an issue. And then we had this nice relaxation, the Kantorovich formulation, which is a little bit harder to understand, but it's perhaps a little nicer to work with in the sense that, one, problems are feasible, which is nice. It's actually kind of a linear problem, which we'll write down and see again in a minute. So we're going to start with that, see what we can learn from here. So this was our Kantorovich problem. So we were looking for the infimo over, now a product space. Okay, we had our cost function, c of x, y, which we're integrating against some measure. Right, this measure was the measure that told us how much stuff moves from x to y. And we don't just want any old measures here. Again, we have some sort of constraint that we're trying to preserve measures. So we want this pi to live in the set that we called capital pi of mu and nu. Do you remember what this set capital pi looked like? It has a set of measures that has proper marginals, right? So what did that mean? Right now, we know that we've started with measures, right? A measure on the set x, which we call mu, and a measure on the set y, which we call nu. And now all of a sudden we've got a measure here that lives on the product space. So we've got to relate it back to things that just live on one of these spaces. So what we said is that if we take this measure and integrate away all the y dependence, so we just integrate over y, now we're left with something that only depends on x, and it had better agree with the measure that we started with on the set x. If we take it and integrate away all of the x dependence, right, we're left with a measure that only depends on the y variable. Again, it had better look like the same measure we started with that only depended on the y variable, this thing we called nu. So we said that pi mu nu is the set of measures whose marginals, okay, on capital X and capital Y are mu and nu, the guys we started with. Okay, one nice thing looking at this is that pi kind of shows up in a linear way here, which is really nice. Is this problem feasible? Okay, some tentative head nods. Why do you think it's feasible? What's that? You could certainly define it to be 0 outside of the marginals. Let me ask this another way. What do I need to be true about my data in order for the problem to be feasible? So if I just give you any two measures in the whole wide world, mu and nu, is my problem feasible? What happens if I give you an example where the total mass is 1 here and 2 over here? Is that a feasible problem? No, right? I can't rearrange this into this. But as long as I've got the same amount of mass here and here, I just have to write down any way of rearranging this into this, and it's automatically feasible. Yes? So this is feasible. It is feasible if we have mass balance. Second question.
Is that taken care of by the condition of, I being a capital sign?
As long as the data actually satisfies the mass balance condition, then yes, this takes care of feasibility. Second question. Are we happy with the first part?
Feasible means the capital value is not empty.
Capital pi is not empty, yes.
Just from a practical perspective, is that always a practical assumption?
Is that always a practical assumption? It's never a practical assumption to just say, here's an optimization problem. I choose to assume that it's feasible. So no, you have to be careful with this. And that's one thing when we wrote down the Monge problem, right, which seemed like a good idea at the time. And then we said, wait a minute, we can write down really simple examples where actually it's not feasible. This set is empty because in the Monge problem we're looking for a map, but as soon as I say maybe I have 1 point here, it's getting split to 2 different points. A map can't do that. So the Monge problem is not always feasible. The reason this is feasible is that I can rearrange things any way I want to. I can let mass go from here to lots of different points. I can spread it out over a line segment or a curve or a volume or whatever. You could actually try to build something explicitly by breaking it down into lots of little one-dimensional problems if you like to, or one-dimensional slits, and sort of taking limits as these epsilons go to 0. And you could actually construct a feasible map that rearranges mass somehow. But yeah, this is feasible because we're allowed to rearrange things and split things. Is there an infimum? Okay, it depends on the cost function. What should be true about the cost function?
Bounded below.
It should be bounded below, sure. So as long as the cost function is bounded below, right, as long as this whole thing is bounded below, the thing that I'm taking the infimum of is bounded below, we're going to have something finite. Okay, so as long as, say, C is bounded below, and maybe we should assume that the space that we're integrating over is bounded.
Okay, if the measure is bounded though, right?
It's okay if the measure is bounded, sure. Then we have an infimum that is finite. In a lot of our examples, although not all of them, C is going to be a non-negative cost. Although it doesn't have to be the case, and in some examples it's not. Okay, so this at least is a problem with a solution, which is a good place to start. Now, there's an even more, something we might care about even more than having an infimum. We might care about, do we actually have a minimum? Right? Can we actually construct a transport plan that actually minimizes the cost? So that is going to be a slightly harder question to answer, but not too bad. So here's our next question. Maybe I'll write it here. Can we find an actual minimizer? So here we need to do a little bit of work. We're going to need to use some kind of compactness argument to argue that actually if we have a sequence that converges to the infimum, that actually the sequence of measures pi converges to an actual minimum. Okay, so we need a compactness argument. Okay, so what we want to do is exactly what I just said, right? We have this object that we can compute for any given pi in this space, in this feasible set. If I compute this, this just gives me a number, right? It's just some real number. So we have a real valued function, and we want to show that we can minimize this real valued function. It's not just find its infimum. We know it has an infimum that's finite. We want to minimize it. So I'm just going to remind you of this. So if we have a function that takes some space x to r, maybe I should not make this x. This is not the same x as over there. We call it u. Okay, I'm going to assume this function is continuous. So I'm trying to minimize a continuous function. And I'd like to show that we've actually got a minimizer. What do I need? I need this space to be compact. So, and if capital U is compact, then we can do it, right? Then F actually attains a minimum. Right? You know it from calculus doing on 1D, right? If you have a continuous function on a closed bounded interval, you're going to have a minimum somewhere in there. Oh, but of course, you've taken analysis and you know that can be generalized, that if we've got a continuous function on a compact set, which in 1D means closed and bounded, then we can do it. We get a minimum. So what does that mean? That means that we need to interpret this. This object here is our F. This space here is our capital U, right? Because we're putting values into it that are pi are things that we're trying to minimize over. So what do we need to do? We need to show that this guy is continuous, and we need to show that this set is compact. And if we can do that, then we're done. Then we've got a minimizer. Okay, so we're going to need a couple assumptions on the data. I'm going to assume, but not too much, I'm going to assume that my cost function is continuous. And I'm going to assume that these two sets are compact. Okay, so this is my claim. Let's suppose x and y, which are subsets of Rn, are compact. So closed and bounded. That's all I mean. And really, I just need them to be bounded. If they're bounded but not closed, I can just kind of extend them out a little bit and say, but I need my measures to be 0 in this extra region. Just don't put mass there. So really, I just need them to be bounded for all intents and purposes. It's a little easier to do it this way. Okay, let's suppose this, and that my cost function is continuous. then the Kantorovich problem attains a minimum. Okay, before I go on to try to prove this, are people actually happy with the statement of this result? Does it make sense? Some people are nodding, some people are avoiding eye contact. Okay, so what are we going to do? I said there's two parts to it. So we're making a compactness argument. What is that? Okay, what is a compact set? Do you guys remember? What's true of a compact set? Every bounded sequence has a convergent subsequence, right? So if I'm going to talk about compactness, I need to say, what do I actually mean by convergence? So before we can talk about compactness, we need a notion of convergence. Okay, we're talking about convergence of measures that live in this set. So here we're identifying capital U with this set of measures. Without loss of generality, I'm going to assume they're probability measures. Total mass is 1. If it's not, you just rescale things. Okay, so without loss of generality, these are probability measures. Okay, what do I mean by convergence? We're going to say that a sequence of measures convergence okay, so gamma n converges to some gamma if okay, the natural way to understand these is sitting inside of integrals just like this, right? So what do I want to do? I want them to sit inside of an integral against some kind of continuous function. So we're going to say that this is true if g of xy d gamma converges to the integral of g against my limiting measure. And this has to be true no matter what continuous function I put here. So this should be for every g that is continuous. This is a reasonable way of talking about convergence here? Okay, so now we said we have two questions. Our first question was, is this set compact? So is pi of mu nu compact? So So what do we have to do? We have to pick any sequence, right, and show that we can extract a convergent subsequence. So let's choose any sequence pi n. So we need to extract a convergent subsequence. In fact, much of the work is already done for us. What do we know about these pi n's? We know they're probability measures, right? So I have a sequence of probability measures that are defined on a compact set. This is already a compact space, right? So this larger space of probability measures is already compact. So I know that I can extract something that converges. Whether it converges to a limit in here, I don't know, but it converges to another probability measure. Okay, so since the pi n are probability measures, they converge, we can extract a convergent subsequence. Okay, so pi sub n sub k, that converges to pi, which is also a probability measure. Okay, so we're trying to write down the definition of compactness. So that said, we start with a subsequence. We need to extract a subsequence that converges to a limit that also lives in the same set that we started in. That's what compactness means. Okay, so what do I need to check? The marginals, right. So I've already found a nice candidate for my limit, which is a probability. We just don't know if it has the right marginals, so we need to check that. Okay, so let's check. Okay, does this pi actually belong to the set we started in? And as is pointed out, we need to check the marginals. Okay, so what do we need to do? We need to check. We need to see what these measures do when we integrate the y dependence away or when we integrate the x dependence away, right? And again, when we're trying to see how these measures behave, we need to integrate them against continuous functions. So let's choose any g. It's continuous. Let's see. Let's just make it continuous on x. We want to somehow try to check the marginal of this thing on our space x, right? And we hope that we recover mu, right? So we hope that if we integrate this against g, that we recover the result of integrating mu against g. So let's integrate. We integrate over x cross y of g of x d pi Okay, what do I know about this integral? Or let me ask this, what do I know about pi? It's a probability measure, yeah. Is it any random probability measure?
It can be written as a sequence of bounded probability measures.
Yeah, it's the limit of a sequence of bounded probability measures, exactly. It's the limit of this sequence of probability measures, right? Okay, so we said this sequence converges to pi, which is what we're interested in, and we said we had to come up with, at the start with, what do we mean by convergence? Convergence means that if we integrate against the elements in our sequence, right, and take the limit, we get the integral of g against our limiting measure. So here is the integral of g against our limiting measure. This should be equal to the limit as k goes to infinity of g integrated against this guy here. So this should be the limit as k goes to infinity of g of x d pi and k. Right? And this works since pi and k converges to pi. That's the definition of convergence. Okay, so that's getting us maybe, hopefully, a step in the right direction. How can I simplify from here? We've got from here to here. Now, what do I know about this integral? The marginals are right? These guys now live in my space capital pi, which means these guys have the correct marginals, which means once I've integrated away y here, I'm going to just be left with my measure mu that I want. So I can right away make that simplification and say this is equal to the integral over x, g of x, d mu of x. And this was because, since we started with something, so the lives in here, so it has the correct marginal. So the marginal over x is mu. And this is good. This is exactly what we wanted to show, right? I wanted to show that if I integrate this against any function, right, the y dependence goes away, and I get exactly what would happen if I integrated against my original measure mu. Right? And we can do exactly the same thing if we swap the roles of x and y. Exactly the same argument implies that the marginal of pi over y is mu. So what did we do? We started with a sequence that lives in the set we care about. We found out that there's a subsequence that converges to some other probability measure, which is good. We have convergence using the notion of convergence that we're talking about. And we did a little more checking and said, moreover, this limiting measure has the correct marginals. And that's all we needed to show that actually the limiting measure belongs to here. So this means that actually the limiting measure is in the set that we started in. So given any generic sequence living in capital Pi, I can always extract a subsequence that has a limit, and that limit also lives in capital Pi. That's compactness. So we know that capital Pi is compact. Any questions on there before I keep going? Yeah.
You said you could relax the assumption of compactness to open sets.
Right, so I'm starting with the bounded sets at least, right? So say I had a measure that's defined supported on an open bounded set. What I can do is say, let's come up with a new measure. I define it on a bigger compact set, but there's zero mass outside the regions that I care about. Okay, and now I have a measure, probability measure. Some places, in some regions, there's no mass. There's some open sets that have no mass in them, but now the whole thing is defined on a compact set. Does that make sense? You look like you don't quite believe me.
No, because I'm trying to think what you get blow up at the boundary. On the boundary.
If you have, right, so these aren't density functions, right? So we could have Dirac's, right?
I'll think about it.
You think about it, okay.
Probability measures.
These are probability measures, right?
At the boundary,
So-
you're not going to have blow up.
These aren't just arbitrary densities, they're probably.
These are probability measures, yeah. So they're not arbitrary functions. So these are probability measures. They're bounded. We don't have to look at their values. So if it happens to be a Dirac mass where there's infinite density at one point, that's fine, right? But we're limited in what they can be, certainly. Okay, we have compactness. Now what else do we need? We need continuity. Okay, so the second thing that I needed to ask was, is my value of f continuous, where f of capital U, right, capital U being this set here, was going to be equal to the integral for x cross y actually, let's call this f of pi. Integral over x cross y of c of xy d pi of xy. Okay, so for pi belonging to this compact set. Okay, so continuity. What's the definition of continuity that I want to make use of here? I want to use a definition that involves limits. So with a limit of what? Okay, so I have some measures that converge to a limit, sure. And what do I want? I want to say that if I have a sequence of pi n's that converge to some pi, then my f of pi n's also converge to f. Right? That's the way of writing continuity. So let's choose any pi n's that live in my space such that pi n's converge to pi, which is also in the correct set. We know it has to be, right, because this is a compact set. And we need to show that that f of pi n converges to f of pi. Okay, so we'll do the obvious thing and write down what this actually is in its full detail. F of pi n is equal to the integral of cxy d pi n we would love to show this converges to f of pi. What do I need to do to show that? Yeah, so there's not really much that I have to do here, right? We started by saying pi n converges to pi. And just given the definition of the spaces that we're working in, the definition of convergence, this is a continuous function. This converges to pi. The definition of convergence of this to pi is that this converges to c of xy d pi. Okay, that's since pi n converges to pi and c is continuous. And we're done. This was a one-liner. Right? This is exactly the thing that we wanted. This is my function f applied to this limiting measure. Okay, so we can say, great, that wasn't too much work. F is continuous. Any questions there? Okay, now we're golden, right? So we came up with a way of formulating this problem where we said, essentially, we're trying to minimize a real valued function over some set. The set is compact. The real valued function is continuous. And now we can pull out this Weierstrass theorem and say, great, we've got a minimizer. Okay, so the Kantorovich problem. Now, the way we've written it down seeks to minimize a real valued function, a continuous real valued function, over a compact set. We can do that, right? So this is indeed possible. So what does that mean? We wrote down this Kantorovich formulation. Remember our original Monge formulation, it was maybe not even feasible. It certainly didn't always have a solution. This formulation has a solution, not only an infimum, but it has an actual concrete minimum. We can write down a transport plan, not a transport map necessarily. We'll get back to when that's possible, but we can certainly write down a transport plan that actually minimizes our transport costs. So if we've got the mines and the factories problem, for example, we can actually write down a transport plan and say, this is the plan, or a plan that's going to minimize the cost for you. Okay, so Kantorovich problem admits a minimizer. Yes?
So the cyclic monotonicity doesn't carry over into the Kantorovich problem?
It does, but you have to generalize a little bit more what it looks like. But yes, you do still have a concept of cyclical monotonicity in here. Any other questions? We don't know what the minimizer is. That's a whole other. We've done some analysis here and written down an existence result. How do you construct the minimizer? And it's not necessarily unique, absolutely. How do you actually construct it in practice is the work of numerics. Unlike in 1D, you're never going to write down an exact solution except for very simple problems. But if you're a numerical analyst, and somebody says, solve this problem for me, at least when somebody gives me a problem, I'd like to know, does it actually have a solution, or am I completely wasting my time here? First of all. Second of all, often there's weak formulations that you need to make use of and respect in your numerics, or there's properties of applications that the scientists actually care about, and you want to be able to build those into your numerics. So actually understanding the analysis can make a huge difference in the type of numerics that you build. And we will start to see that later in the semester. I'm going to leave you there. We're going to play more with the Kantorovich problem in the next lecture or two and see what else we can learn. Eventually get back to why does this tell us that actually the map we're looking for somehow looks like the gradient of a convex function. But for now, I leave you there.